Hey everybody, this is Mr. Bortnick for AP Calculus AB. We're in Unit 5, Analytical Applications of Differentiation. Today we're doing the Chapter 5 End of Unit Review, which is focusing on reviewing sections 5.8 through 5.12. We will be using a calculator today, so you want to get your TID3 or TID4 out, and just some reminders that we always use radian mode in AP Calculus, and if you're rounding, round to 3 digits after the decimal place. Enjoy today's notes. All right, for the end of Unit 5, we've got a series of problems we're going to go through. I'll mention the first two problems are going to be calculator active problems, so I'll show you how I would do these on the calculator. Let's get started. So, Chapter 5, number 1, the first derivative of the function f is given by this equation. How many points of inflection does the graph of f have on the interval from 0 to pi? Now, we notice that they gave us the first derivative, so we know that this is the first derivative, and we know that points of inflection are places where the second derivative changes signs. So, places where the second derivative changes signs, and they're asking us to count how many points of inflection does the graph of f have. So what we're going to do is we're going to go to our graphing calculator, and let's do that now. Once we've got our graphing calculator ready to go, we're going to use it to help us find out where the second derivative is changing signs. So what I'm going to do is I'm going to go to the y equals screen where I've actually already typed the equation in. What I'm going to then do is I'm going to go down to y2, and I'm going to have it graph the derivative, right? This is already the first derivative, but we need to know where the second derivative changes signs. So I'm going to go to my math menu. I'm going to go to nderiv, which is the number 8, and it's going to pull up our formatting here for the derivative. So I'm going to take the derivative with respect to x, and instead of typing this whole equation in, what I'm going to do is I'm going to go to my variables, and I'm going to go to my y variables. I'm going to hit function, and I'm going to have it pull the equation that's in y1. So now, whatever equation I have that's in y1 here, it's going to be taking the derivative of it here in y2, which is pretty nice so that I don't have to type all of that back in again. And again, the shortcut for that is to go to the variables button, to go to yvars, function, and then y1 for that. So we've got that in, and then we're going to say that in our derivative statement that x is going to be equal to x, so that it graphs the whole line for that. Next, before we get to the graphing part, I'm going to actually turn this equation off. So at this equal sign, I'm going to press enter, and now it's no longer highlighted anymore like it is, which means when I graph it, it's not going to show this first line. In this problem, they also told us that we only care about x values between 0 and pi, so I'm going to make those that my x min and my x max. And I, again, also really only care where the second derivative is changing signs. So I'm looking for y values around the x-axis, so I'll go from -1 to +1 on the y min and the y max. Once I've got that, I'm going to graph using this window, and we'll see what we've got. So this red line looks like our derivative, our second derivative, and so it clearly looks to me like it's crossing 1 time, 2 times, 3 times, 4 times. I'm sure if we zoomed out, we'd see maybe something that looks like this, that's going down and then back up and then something like that. But it is changing sign 4 times, which means that this function is going to have 4 points of inflection. Okay, so using our calculator, we're able to see that there are going to be 4 points of inflection. 4 points of inflection for the f of x function. Since we were taking a look to see how many times f double prime change signs on the interval from 0 to pi. Really nice that you can change the window to just see exactly the part that you're looking at. Very useful. Number 2, calculator active problem. The rate of money in a particular mutual fund is represented by M of t. So key pieces here. We have this M of t, and they're telling us already that that is the rate of money in the particular mutual fund. So I'm looking a lot at that word rate. In thousands of dollars per year, where t is measured in years, is the amount of money from this mutual fund increasing or decreasing. So since this is already a rate, we don't need to take a derivative. Really, when t equals 4, I just need to know what m of 4 is. And so in my calculator, I'm going to want to just plug 4 into this equation, no derivatives, nothing like that. And so essentially, we're doing sine of e over 3 raised to the 4th power. If you do that on your calculator, that's just basically plugging in. You should get something that rounds to about 0.384 for this. And our conclusion then, once we know that, is that since m of 4 is positive, the amount of money is increasing. Because that derivative, or not even the derivative, but the rate is positive. Since this was a rate, we didn't need to take a derivative. It's already the rate. If they didn't have that word in this, then I would have to take the derivative and then plug in to find whether it's increasing or decreasing. But this is essentially telling us that this is already a derivative of something. Cool. Number 3, a particle is traveling along the y-axis and its position from the origin can be modeled by this equation. On the interval from 0 to 2, when is the particle farthest above the origin? So keyword, we're talking about farthest. This is essentially asking us to find a maximum. When is it the maximum for this? With that said, we know that maximums and minimums occur when the derivative, they occur at critical values. So that's where the derivative is equal to 0 or it's undefined. So let's find the velocity of this position function. That's going to be the derivative. So 6 minus 6t squared would be that derivative. And we can try to figure out where that's going to be equal to 0 to find those critical values. So 6 minus 6t squared equals 0. 6 equals 6t squared. So 1 equals t squared. So that means that t equals 1 or negative 1. Now, because we're trying to find the maximum and they gave us endpoints here, we need to consider both the critical values and the endpoints. Now, we also need to be careful here that they said that t is between 0 and 2, which means that actually negative 1 does not matter. We don't care about negative 1 since it's not on the given interval, but 1 is the critical value that's on that interval that we care about. So what we're going to technically do is what's called the candidates test. We're going to just plug in, so the candidates test, we're going to plug in our t-values into the equation, and we're going to just see what happens. So the t-values we're looking at are 0 and 1 and 2. 0 and 2 came from the endpoints over here. 1 comes from the critical value that we had here. So that's where we're figuring out what needs to be in this table. And then we're going to just plug that into the original equation, y of t, to determine how high or how low that function is going to be. If we do that, we're going to get outputs that are 10 and 14 and 6. And so if we're trying to find the maximum, we're going to pick the biggest one of these. That appears to be occurring when t is equal to 1. And they're asking here, when is the particle the farthest above the origin? So our conclusion is going to be at t equals 1, the particle is farthest above the origin. And that's our conclusion for part A. For part B, on the interval from 0 to 2, what is the particle's maximum speed? So again, speed, we remember, is the absolute value of velocity. And if we're trying to find the maximum of velocity, if we're trying to find the maximum of that, we're going to need to take a look at the derivative of velocity, which means we're going to need to bring out our acceleration. So the acceleration is going to be, looks like negative 12t. And we want to know possible places where this is going to have critical values, where this derivative is going to have critical values. So that's going to be when this is equal to 0. And that looks like that's at t equals 0 for this. So the possible places that we could look at for our maximum speed are going to be at the endpoints, 0 to 2 again, or this critical value, which is also 0. So this one we only have 2 points to test. Again, we're doing our candidates test, and we're going to just plug in those values. So t, and then we're talking about the velocity, so we're going to do v of t. And so 0 and 2 are our 2 values. If we plug in into our velocity equation from part A, if you plug in 0, you get 6. If you plug in 2, you're going to get negative 18. And we remember here that the speed is going to be the absolute value of these. So the speed here would then be 6, and here it would be positive 18, because you cannot have negative speed. We just have speed in the negative direction. And so the biggest one appears to be when t equals 2. So what is the particle's maximum speed? So the maximum speed is 18. And what are our units here? Looks like meters per minute. At t equals 2 minutes. That's going to be our answer for part B. Let's move on to number 4. Rectangle is formed with the base on the x-axis and the top corners on the function 36 minus x squared. What length and width should the rectangle have? So that's area is a maximum. Nice. This to me looks like this is going to be the top half. It's going to be a semicircle with radius 6. And so if we take a look at a picture of this, thinking about 6 and 6 and 6, we essentially have this semicircle. And we've got our rectangle that the base is on the x-axis. So I have some rectangle, and then its sides are going up to that circle. So the top corners are on the function. What length and width should the rectangle have so that's a maximum? So since this is from the origin, that means that the distance from here to here is going to be x, and that would be x as well. And then the height of this is going to be whatever the height of the function is. So that's going to be 36 minus x squared for that. So if we're trying to find the maximum of this rectangle, we know that the area of a rectangle is going to be the length times the width. So the length of this rectangle looks like it's going from one side of the rectangle will be going from here to here. So x plus x is 2x. And then the width of that rectangle, or the height of that rectangle, is going to be 36 minus x squared. And so now that we've got this equation set up, let's distribute it and say that this is what? 72x minus 2x cubed. If we're going to optimize this and find the maximum area for it, we're going to have to take the derivative. So let's do that. A prime is going to be 72 minus 6x squared. And we know maxes and mins occur at critical values, so places where the derivative is 0 or it's undefined. So let's say that 0 is equal to 72 minus 6x squared. That means that negative 72 is equal to negative 6x squared. If we divide, that means that 12 is equal to x squared. So x is going to be equal to the square root of 12. So if we're trying to find, they're asking us then what is the length and the width that the rectangle should have. The math lead in me says let's simplify this. We know we could break this square root down to be to the square root of 4 times the square root of 3. So that's 2 root 3 for that side length. But the length of that rectangle is going to be x and x. So x times x, which is 2x. So the length should be 2 times 2 root 3. So that is 4 root 3 for the length. And then the width should be 36 minus 2 root 3 squared. So that looks like that's going to be 36 minus 4 times 3, so minus 12 is going to be 24. And so our length is going to be 4 root 3. Our width is going to be 24. So those would be the values that this rectangle would need to have in terms of length and width to optimize and maximize the area if it's constrained that its corners have to be on the circle. That is the most area that you could possibly have. And I do want to step back and just mention, I didn't show any sign changes or anything like that. When we found 2 root 3, this was the critical value, and it was the only critical value. So because it was the only critical value, it's the only place that this could have had a maximum. So I didn't need to check anywhere else. And so that is our justification for number 4 and our solution for number 4. Let's try number 5. The graph shows the derivative of f prime. Identify the intervals when f is increasing and decreasing, include justification statement. So again, this is the derivative of f. This is f prime of x. Nice. Where is f increasing and decreasing? So key piece for this, we know that f is increasing when the derivative is positive. So I will highlight that in green, these places where this function is increasing. F of x is increasing because f prime is positive. So that looks like that's occurring to me between x equals -3 and x equals -1, and from 3 to infinity. And we can say that is since f prime of x is positive on those intervals. If we switch to decreasing, we can see where f prime of x is below the x-axis. So to me, that looks like it's going from -infinity all the way up to -3, and from -1 up to +3. And that is since f prime of x is negative. So again, we know that the derivative, the output of the derivative, is the slope of the tangent line of f of x. And so if the slope is positive, it's going to be increasing. If the slope is negative, it's going to be decreasing. Number 6, for the table below, selected values of x and f of x are given. Assume that f prime and f double prime do not change signs. Is f of x increasing or decreasing? Okay. So since we know that the f prime and f double prime don't change signs, and we only have this information here, to think about f prime, I'm going to first notice that each of these is going up by 1 on this side. It's a consistently going up by 1 on the left side. And then we notice that on the right side, this is going up by 2, then by up 3, then by up 4. So this is essentially our f prime of x. It's not exactly the derivative. It's almost like it's an average rate of change, pretty much. And that average rate of change is positive, so I would say that f of x is going to be increasing on that interval. To figure out concavity, we're going to look at the changes of the changes. So that is going to be increasing by 1 and increasing by 1. Essentially, we're thinking about f double prime by doing that. And so we know that this is going to be concave up, because the second derivative is positive for that. Great. Number 7. Given the function g of x is equal to -x to the fourth plus 2x squared minus 1, find the intervals when g is concave up and decreasing at the same time. So this is one of those ones where we could, you might make two separate tables. We had a lesson recently where we combined them into one. So let's first find the critical values, places where the derivative is equal to 0 or undefined. That's -4x cubed plus 4x is going to be our derivative. We can factor out, that looks like a, -4x times x squared minus 1. So that's going to be -4x times x plus 1 times x minus 1, since we get a difference of 2 squares. And so that tells me that my critical values are going to be -1, 0, and 1 for this one. So we've got critical values first. Next, now that we've got our g prime, let's find g double prime and find those possible points of inflection. So that's going to be -12x squared plus 4, which again I'll factor out. Actually, doesn't look like we can factor anything out. We're going to just set that equal to 0, since this can't be undefined. So let's say 0 is equal to -12x squared plus 4. So -4 is -12x squared. So 1/3 is x squared, which means that x is plus or minus the square root of 1/3, which, if we wanted to go any further, could be plus or minus the square root of 3 over 3, if we rationalize that denominator. So these are our possible points of inflection. Let's say POI, points of inflection. All right, so now that we've got that, let's get this table happening. Actually, looks like we're going to need a bunch of room, so maybe I'll just go down here and do this with number 8, since that looks like a multiple choice problem. So I'm going to set up this big old table. In this table, we're worried about 3 things: x, g prime of x, and g double prime of x. And on this, I need to make sure that I have each of the critical values and each possible point of inflection. So I'm going to have 5 x values on here with some spaces for each of these. So let's do -1. We'll do -√3 over 3. We'll do 0. We'll do positive root 3 over 3. And then we'll do 1. And then we'll have that space to the right of it. Okay, so we've got all of this. Whew, lots of stuff. Let's see what we know, and then we'll fill in the intervals to the side of this. So at -1 and 0 and 1, we know the first derivative is 0. And at negative root 3 over 3 and positive root 3 over 3, we know that the second derivative is 0, since those are places where the second derivative was 0. And then let's get our intervals on here. So all my values less than -1, that's going to go from negative infinity to -1. Then we've got -1 to negative root 3 over 3. Then negative root 3 over 3 to 0. Then 0 to positive root 3 over 3. Then root 3 over 3 to 1, and then all the values greater than 1. All right, so lots going on here in this table. So what we would need to do then, we're going to need to go through the first derivative and then plug in values on these test values to determine if it's positive or negative. In this case, if we take a test value that's less than -1 and we plug it in for our g prime, we're going to see that this is positive on that interval. If I pick a value between -1 and 0 and I plug that in, we're going to actually have negative values for the first derivative there. Then if we do positive between 0 and +1, if we plug in a number, those are going to be positive on that interval. And then it goes negative again when you pick a number bigger than 1. For the second derivative, again, pick a number on this interval, each of these intervals, and plug it into our second derivative. If we do that, we're going to have negatives on this interval, positives on this interval, and negatives on this interval. So, again, the work for this is maybe like showing that, like doing the test points or thinking about how these functions look to determine whether they're positive or negative. But, I would also say if you're not comfortable with trying to do this like giant big table, it's totally fine to do 2 separate tables and then just compare them. But we're looking for something that's concave up. So concave up means that the second derivative needs to be positive. So I'm looking at these values here, and then we're also looking to see where this function is decreasing. So we're looking to see where the first derivative is negative. So it looks like there and there. So the only places where that occurs to both be happening looks like that's going to be right here, where we have a negative first derivative and a positive second derivative. So g is concave up and decreasing on the interval from negative root 3 over 3 to 0, since g prime of x is negative and g double prime of x is positive. That would be our justification looking at this table. Those are the only places where both of those things are happening at the same time. Great, that's number 7. Number 8, I've already written a bunch here, but let's take a look at the problem itself. Luckily, this one's multiple choice. The mean value theorem can be applied to which of the following functions on the closed interval from 0 to 5, from 0 to 5 here. We know that for the mean value theorem to apply, that it needs to be continuous and differentiable on the given interval from 0 to 5. In this case, if we take a look at this, think about this function, this radical, or not radical, well, it is technically a radical, but this exponent raised to the 2 over 3 power, it's going to have a cusp on this. This is not differentiable for b, so that won't work. And we can see that for c, that at x equals 3, this is going to have a asymptote. It's going to be discontinuous. And so this is not continuous, which means that the mean value theorem wouldn't work. And then we know that this absolute value is a classic cusp, which looks like it's going to be happening at 4. And we know that cusps are not differentiable. So these is not possible for any of those 3 that we could use the mean value theorem. The only one that we could use the mean value theorem on is A here. And that is, again, because that's the only one that's continuous and differentiable on the interval from 0 to 5. We do see that this would have a discontinuity, but it has a discontinuity when x equals -3, because we'd be dividing by 0. And so that has an asymptote at -3, but that's not on the interval from 0 to 5. Number nine. We're moving on to the next page of this. To the right is the graph of h prime of x. Identify all extrema of h of x. No justification needed on this problem. So we know that extrema of h of x occur at critical values, or they could occur at critical values, but where the sign change. And we know that critical values are places where the derivative is equal to 0. So it's where it hits the x-axis. So I'm seeing that these four spots, -2, 0, 1, and 3, are critical values. How would we determine the extrema and what type they are? Well, we need to look at the sign and how it's changing of that derivative. We see at -2, it's going from negative to positive. That tells me that this is going to be a minimum. Here at x equals 0, we see it's going positive to negative, so that is telling me that that's going to be a maximum. Then we have negative to positive, so we have a minimum again. And then here we have positive to positive, which is neither. Nothing is happening at x equals 3. So to conclude, no justification is necessary. Well, I've explained it verbally, but we know that there is a min at x equals -2. We've got a max at x equals 0, and we've got another min at x equals 1. So that would be our conclusions for this. If we did need to justify on this, we would reference the fact that how the derivative is changing from negative to positive, how it's switching signs. Negative to positive would be a minimum, positive to negative would be a maximum. Number 10, the derivative of g is given by this function. For x is greater than 0, find all relative extrema and justify your conclusions. So first off, I don't like this negative exponent. I'm going to rewrite this as 5 minus x to the x cubed, divided by x cubed to make that positive. And so relative extrema are going to be when this they occur at critical values. They occur when f prime or g prime in this case is equal to 0 or it's undefined. So where are the critical values for this? Well, we can see that it's going to have critical values at x equals 5, since that would make this denominator equal, or rather this numerator equal to 5, and so this would be a derivative of 0. Or we could have the denominator be equal to 0 and it would be undefined, so that would happen at x equals 0 for this, right? Because we'd be dividing by 0, it would be undefined, and so that's a possible place where we might have extrema. With that said, though, we want to take a look at a sign chart for this. So our sign chart, we're going from x, we have g prime of x. We just want to see, how is the derivative changing signs so that we can identify that extrema and justify our conclusions. We've got 0 as one of our values, we've got 5 as the other value, and then we know that the derivative is undefined at 0, and it is 0 at x equals 5. And we can add in our intervals going from well, actually, in this case, since x is greater than 0, this is actually not on the table. But we do have from 0 to 5, and then we've got all the values bigger than 5, so 5 to infinity for that. From there, if we plug into our derivative, let's plug in 1. Let's see what happens. 5 minus 1 is 4. 4 divided by 1 cubed is a positive value, so we've got a positive here. If we pick a number bigger than 5, like 6, we have a negative divided by positive, so that's going to be a negative. So what do we have? Well, in this case, the only thing that could be a extrema here would be at 5, since we don't have, since it's not defined for values less than 0, and in fact x can't actually equal 0 for this. The only value that we see here is at 5. So let's write that out. That g has a, what does it have? Well, it has a maximum at x equals 5, since g prime of x changes sign from positive to negative. So g has a maximum at x equals 5 since g prime changes sign from positive to negative. That's going to be our answer for number 10. Number 11, consider the function f defined by f of x is equal to e to the x times sine of x with domain from 0 to 2 pi. Find the absolute maximum and minimum values of f of x. So keyword here, absolute, and also the fact that they gave us an interval just means that we need to consider also endpoints in what we're doing here, in addition to just the critical values. So our critical values are going to be places where the derivative is equal to 0 or it's undefined. This looks like we're going to need to apply the product rule for it. So if we do that, that's e to the x cos x plus e to the x sine x would be our derivative for this, which we could factor out and say is e to the x cos x plus sine x. And we want to know where that derivative is equal to 0. So e to the x can't equal 0, right? It's there's an asymptote at a height of 0, so that would not work. So we're looking for places where cosine of x plus sine of x is equal to 0. So cos x plus sine x equals 0, which would be places where sine of x is equal to negative cosine of x. So how would we think about that? We're trying to think about places where the outputs on the unit circle are opposites of each other. And if we think about our unit circle, the only times when the sine and cosine have the same sort of value, if we don't take into account the sine, are going to be the like pi over 4, the 3 pi over 4, the 5 pi over 4, the 7 pi over 4. And in fact, if we do it over here, if we think about our little unit circle here, there are two places, specifically at 3 pi over 4 and at 7 pi over 4, that the values on the unit circle are going to be negative root 2 over 2, comma, positive root 2 over 2, and then this is going to be positive root 2 over 2, comma, negative root 2 over 2. So we can see in these two cases that they're the same value, just opposite signs, which is essentially what we're asking for here. So our critical values then are going to be at those x values, at 3 pi over 4 and at 7 pi over 4 for that. With that said, though, we do need to essentially do the candidates test here and take into account the domain that was given to us. And so we're going to plug in x and our original function f of x, and let's use the values that they gave us. So 0 and 3 pi over 4 and 7 pi over 4 and 2 pi would be the values that we've got. You could plug in into your, well, this isn't a calculator problem, so we would need to plug into our original equation. Here we've got what? E to the 0 times sine of 0, so that's going to be 0. Probably not the maximum, but maybe the minimum. Then we've got at 3 pi over 4 and at 3 pi over 4 we've got e to the 3 pi over 4 times sine of 3 pi over 4. Sine of 3 pi over 4, if we take a look at our unit circle, is going to be root 2 over 2. So that's going to be equal to root 2 over 2 times e to the 3 pi over 4. For 7 pi over 4, we've got e to the 7 pi over 4 times the sine of 7 pi over 4. At 7 pi over 4, sine is the y value. That's negative here. So that's going to be equal to negative root 2 over 2 times e to the 7 pi over 4. And then at 2 pi, we've got e to the 2 pi times sine of 2 pi. Sine of 2 pi is going to be 0, so that whole thing's going to be equal to 0. So what do we see? We see that we've got these 0 outputs at 0 and 2 pi. Here we have a positive value that's bigger than 0. Here we have a negative that's lower than 0. So that's sort of telling me that this is going to be the max is going to be at 3 pi over 4. And the min is going to be here because that's the only negative value that we've got, which is going to be at 7 pi over 4. And they are asking for the actual values themselves, so we would want to make sure that we are saying what those are. If I had a little bit more room, I'd probably write a justification statement, but I am already writing pretty messy. Sorry about that. But those are the values of the maximums and minimums, and they occur at x equals 3 pi over 4 and at 7 pi over 4. Cool. Number 12. Using the figure below, complete the chart by indicating whether each value is positive, negative, or 0 at the indicated points. For these problems, if the point appears to be a max or a min, assume it is. Great. So at A, this is a graph of f of x. So at A, f of x is below the x-axis, it is negative. Let's do all of the x-axis here, all of the f of x's here. B is above the x-axis, so it's positive. C is above the x-axis, so it's positive. D is on the x-axis, so it's 0. E is positive, F is positive, G is positive, H is negative, I is negative, and J is on the x-axis. So for this row, all I'm looking at is the output of this function positive or negative? Is it above the x-axis or below the x-axis? For the first derivative, I need to look at the slope of the tangent line. So at A, I notice if I draw a tangent line, that slope is positive. If I draw a slope at B, that slope is positive. If I draw a slope at C, that slope is negative. At D, that has a slope of 0. At E, it has a positive slope. F has a 0 slope. G has a negative slope. H has a 0 slope. I has a positive slope. And J has a very positive slope. So that is what I'm looking at for f prime, because we know that f prime is the slope of the tangent line. So you can either imagine the tangent lines, or you could draw your own little tangent lines on these. Cool. That is the first derivative. Second derivative is essentially concavity. We know that the concavity of f of x is controlled by the second derivative, and I know that when f of x is concave up, that f double prime is positive, and if f of x is concave down, then f double prime of x is negative. So what am I noticing? Well, I noticed that on this interval from here to here that this looks sort of n-shaped from there to there, that looks like that is concave down to me, which means that the second derivative at a and b would need to be negative. C sort of, it looks like this point where the concavity is switching from being concave down to concave up. This is what we call a point of inflection. It's a place where the second derivative would be equal to 0. At the next point, we sort of see that it looks like this is more U-shaped from here to here. So I would say that at D, that likely that is positive second derivative since it's concave up. And then from at E, it looks like maybe another point of inflection where that concavity is switching from being concave up to concave down. And then we look like we've got something concave down through F and G till maybe about right there. So negative second derivatives, at which point it switches to being U-shaped again, concave up for H, I, and J. So that is how we'd fill out this table, and of course, we could justify all sorts of things that are happening on this. Yep, that's our table for number 12. Number 13, multiple choice question. The graph of f is shown below. It's f. Which of the following could be the graph of the derivative of f of x? Okay. Well, what do we notice about the derivative? We know that the derivative is the slope of the tangent line. At x equals a, this looks like it has a horizontal slope of 0. Then I see that it has a positive slope. Then I see it has a slope of 0. Then I see it has a slope that's negative. Then I see a slope of 0. So I'm looking for a function that starts at 0, it goes positive, it hits 0, it's negative, and 0 again. So 0, positive, 0, negative, 0. That looks like right immediately the answer to me. This is going 0, negative, 0, positive, so that's the opposite of this. This is never negative, so that would not work. Here we've got a positive value up here, even though the slope should be 0 at A, so that's no good. And then, I don't know what this is. It's not 0 at A or B. So A is our only answer that makes sense for this particular problem. And that's it. The answers are actually on this sheet as well, in case you were working along at home. But hopefully that was helpful for you. Good luck on your Chapter 5 end of unit test. Stop by in class with any questions. Come on by office hours and do some review on your own. I hope the test goes well for you. Good luck.